Have you ever just stopped and stared at a math problem and thought, wait a second, why is that true? Well, today we're tackling one of those exact questions. We're going to look at why the square root of 2 and the number 2 raised to the power of 1/2 are the exact same thing. I mean, look at them. They don't look anything alike. But as you're about to see, this isn't some random coincidence. It's a really cool piece of mathematical logic.
Okay, so here they are, side by side. On the left, you've got the classic square root of 2, that familiar symbol we all learned in school. And over on the right, you have 2 with a little 1/2 floating up there as an exponent. It's kind of weird, right? You'd be forgiven for thinking it just means half of 2. But nope, these two totally different looking things represent the exact same number.
So that's our big question for today. How is this possible? Is it just some arbitrary rule that a mathematician made up centuries ago that we all have to memorize? Or is there something deeper going on, a more elegant logic at play? Well, that's exactly what we're going to dig into.
Right, so let's treat this like we're solving a mystery. We're not just going to jump to the last page of the book and read the answer. We're going to follow the clues.
Because that's the key thing to remember here. This is no accident. It's a beautiful example of how math is a language. And like any good language, it's built on consistency. Every symbol, every operation, it's all designed to work together. And if we can learn to read that language, we can solve this whole thing.
Okay, so first things first. Let's start our investigation with the piece of evidence that's probably a bit more familiar to all of us, that classic square root symbol. So what does this symbol actually mean? Well, at its heart, a square root is really just a question. When you see the square root of, say, 9, the question it's asking is what positive number, when I multiply it by itself, gives me 9? And of course the answer is 3. So the square root is the operation that undoes squaring.
And this isn't just some abstract idea floating around in space. It's real. Take a simple square where each side has a length of 1. If you measure the diagonal from corner to corner, its length is literally the square root of 2. It's a real physical length you could, in theory, measure with a ruler.
Now hold on. Before we go any further, we need to clear something up. This is a huge point of confusion for so many people. Reading a to the 1/2 power as half of a is a super common mistake, but it's totally wrong. Just look at the example. 9 to the 1/2 power is 3, but half of 9 is 4.5. See? Completely different things.
Okay, with the root symbol pretty well understood, let's turn our attention to our other suspect, that little fractional exponent. And to get what it's all about, we have to look at the fundamental grammar of how all exponents work.
You know, these are the basic laws of the land for exponents. You've probably seen them before. But the one we really need to laser focus on today is this one right here in the middle, the power rule. It just says that when you raise a power to another power, you multiply the exponents. This rule is everything. It's the key that's going to unlock this whole puzzle.
And here it is. This is probably the most important idea in this entire explainer. When mathematicians come up with new ideas, like these weird fractional exponents, they don't just invent a whole new set of rules from scratch. No way! The number one goal is to make sure that all the old established rules, like our beloved power rule, still work perfectly. The system has to stay consistent. You can't just break the rules. So that single idea of consistency, that brings us right to the moment of truth. We're not going to just look up the definition. We are going to use pure logic to figure out what that 1/2 exponent has to mean.
So let's ask the right question. We're not just asking, what does it mean? We're asking if we demand that the power rule we already know and trust has to keep working, what is the only possible meaning for a to the power of 1/2?
All right, let's try it. Let's just take our mystery expression a to the 1/2 power and square it. What happens? Well, if the power rule still holds true, we have to multiply the exponents. So what's 1/2 times 2? It's just 1. So we end up with a to the power of 1, which is, just a.
And there it is. That's the big reveal. We just showed that this weird thing, a to the power of 1/2, is the number that when you square it gives you a. Well, that sounds familiar, doesn't it? It has to be the positive number whose square is a. Logic gives us absolutely no other choice.
And this just lays it all out perfectly. On the left, that's the definition of the square root we started with. And on the right, that's the meaning that the rules of logic forced upon the 1/2 power. They are exactly the same. They mean the same thing, not because someone decided they should, but because of careful, consistent, logical design.
You know, what's really cool is that this isn't just some clever one-off trick that only works for square roots. This elegant logic is how the entire language of math grows and expands to include new ideas.
You can run this exact same play for any root. What about a to the 1/3 power? Well, if you raise that to the 3rd power, the exponents multiply to 1, and you're just left with a. So a to the 1/3 must mean the cube root of a. The pattern holds up perfectly, no matter what fraction you use.
Let's just make that concrete for a second. 8 to the power of 1/3. That's just another way of writing the cube root of 8. We're just looking for the number that when you cube it gives you 8. And that number, of course, is 2.
So, in the end, the square root symbol and the 1/2 power aren't two different things at all. They're just two different ways of writing the exact same idea, born from this powerful need for a single, consistent mathematical language. It's not about memorizing random rules, it's about understanding the why behind them. So the next time you see a fractional exponent, I hope you don't see something confusing. I hope you see a little piece of that beautiful, inescapable logic that makes math work.